I thought I muted it.
No, we could see it though.
Okay, okay.
So I would like to welcome everyone watching to this last and hopefully the best webinar by Dr. Rudy Montez. He is a astrophysicist at the Chandra Director's Office of the Chandra X-ray Center at the Smithsonian Astrophysical Observatory in Cambridge, Maryland, Massachusetts.
Yes.
He has his Bachelor's of Arts in Astronomy from the University of Texas at Austin, and his Bachelor of Science in Physics in 2003 from UT Austin. He has completed a PhD in Astrophysical Sciences and Technology in November 2010 at the Rochester Institute of Technology. We are thrilled to have him here giving a seminar today. The seminar series is supported by the University of Central Arkansas's Foundation and the So please take it away, Dr. Montez. Thank you for being here.
Thank you for introducing me and having me. Let me share my screen. Can you all see that?
We did for an instant, and now it's back to you.
Uh-oh. Oh, I remember we have to full screen first and then screen share.
Right, right.
Or share my desktop. That good?
That's it. Perfect.
That's it. Excellent. Excellent. Okay. So thanks a lot. Again, it's great to, well, I could see you all earlier, but now I can't see you, but that's okay. So we're gonna learn today a lot about how stars in their lives and stars in particular that are stars like our sun. So I have it here in my title, sun-like stars, because I'm talking about stars that are about 1 to 8 times the mass of our sun, and we call those sun-like stars. You may have heard of more massive stars and how they end their lives as neutron stars and black holes. These are not the stars that do that. These are the stars that end up as what you see here, which I'll explain to you. And by the end of my presentation, you should be able to understand what we're looking at in this image. And then I'm going to focus today a lot on what we have learned from space-based observatories, so satellites that we've launched into space and that have been studying the cosmos for decades. We'll touch on a broad range of observations across the electromagnetic spectrum, so everything from visible light that we can see with our eyes, all the way to X-ray emission that we can't see with our eyes, and that fortunately for us, we're protected from by our atmosphere, which is also why we have to go into space to actually study the X-ray emission from these objects. So without any more hesitation, I'll start and just tell you what you're looking at. I'll spend some time on a couple of these images because I want you to really understand what it is that we're seeing in this image. So this is called the Helix Nebula, and this is an image taken by the Hubble Space Telescope. It's actually comprised of several images. This was a fortuitous, or I should say, yeah, fortuitous for people who study these types of objects, time during the Hubble Space Telescope's life when there was a debris field that the space telescope was passing through. And so in order to protect the telescope, the Hubble Space Telescope, they pointed it away from the debris field. And so it was pointed so that essentially the back of the telescope was plowing into the debris field. And it just so happened that the direction it was looking was this object. And so because they weren't actually going to be doing normal observing during that time, somebody had the wise idea to just image what it was looking at. And so this is actually comprised of a bunch of images. Each Hubble Space Telescope field takes up a really small part of this image. So there are probably about 20 to 30 images from the Hubble Space Telescope that go into comprising this entire image. And what you're looking at is a bunch of gas and a bunch of stars. You see a lot of stars, the points of light spread throughout the image, but there's one in particular that's particular to this object, and it's that star in the middle, that star in the center of all of this gas. That little white dot is essentially what was once the core of a star like our sun. And so right now our sun is pretty big. We'll say it's a solar radius. It's very important to us. And it has about the mass of a sun. But the star that you're seeing in the middle of this object is about half of that size in mass, and about a tenth of the size that the sun is today. So half the mass crammed into an even smaller amount of space. And so it's a very dense object, and we call those objects white dwarfs. Later on, I'm going to show you the path that we get from our sun to this stage via a diagram that I hope will illuminate what's happening, the physics and stuff that's happening there. But so all of this gas that you see around this star, you can see in this image, you see little rays of material that seem to all be pointing towards that central star. So towards that central star in the middle, that white dwarf. All of this material has been shed by the star. So all of the red, yellow, blue that you see in this image was once the star, was once the sun, was once essentially like our sun, all that gas. It was once all contained in this nice, well-behaved star. And then it shed all of that material, and that's what we're looking at now in this image. And these colors are actually pseudo colors, so they're made to be this color, but what we're actually looking at in each color is actually the chemical properties of that material around this dying star. So the red color in this image is actually the hydrogen gas, so it's mostly focused on an H-alpha emission line. And so what that essentially means is that there's a bunch of hydrogen atoms around in this gas, and when they get excited, they knock electrons into higher shells, and those electrons, when they decay back to a lower shell, emit a photon. And those photons have very characteristic energies or very characteristic wavelengths of light that they emit. And that's what we're looking at in this image when we see red. That's where the hydrogen is. The yellow is probably indicating where nitrogen is, and the blue is probably indicating where oxygen or helium is. So all of these chemicals, they don't exist. They exist in the star to some degree, but they don't exist in this gaseous phase until they have been ejected from the star. So in the beginning, this gas and material is typically just really high temperature and completely just plasma. So here's another image, also from the Hubble Space Telescope, called the Spirograph Nebula. I guess that maybe a lot of you are too young to know what a spirograph is, but if you did, it's a little apparatus that lets you draw these interesting structures. And this planetary nebula kind of resembles the type of image you might get. And this is, I want you to notice how you really see this really sharply defined outer shell. You don't see this fluffy material like you saw in the previous image. Instead, you see a nice oval shape. And then in the center, you see a blue oval shape that's surrounding, once again, a star in the middle of this material. And again, that star was just like our sun and has now shed all that material into the circumstellar environment. Here's another beautiful image, another oval, another central star, another inner rim of material, and then this outer fluffy material. And then in this object, you see these red flares of material that seem to be spewing out. And when you actually measure the velocity of that red material that you see in this image, it's actually traveling at a faster velocity than the rest of the material, suggesting that it has been ejected at a later episode. This object is called the blinking nebula, not because the nebula, which is all of the gassy material, not because the nebula blinks, but because the star in the middle blinks. And that's important, an important point that'll come up later in my presentation. This is the Eskimo Nebula, and you'll notice here again a nice outer shape of fluffy, fuzzy material, and then this inner shell, and then again the central star. And here's the famous Ring Nebula, which many of you, if you ever have an opportunity to look into a telescope, can actually see with your naked eye. It won't look as impressive as this image. It'll look more kind of dull green and gray, actually, but it's really quite spectacular to look at it. It's, if you've ever seen one of these little glass squares where someone has etched something inside of it and it looks like an image, the Ring Nebula looks like one of those when you're looking at a telescope, and it's really, really bizarre and really makes you think about how amazing these discoveries must have been in the beginning, before we had images like this. So you'll see in this image as well, you'll see a lot of these dark spots of material that seem to be pointing back to the central star. And those are all important points that we'll come back to when we talk about the physical process that explains these objects. So here's the Little Ghost Nebula. And I always tell people I'm really excited about the work that I do because I get to look at beautiful images. And it's a really rare treat to be able to do that. Typically, when you're studying objects, you're studying stars, or you're studying objects that are so far away that you don't actually get to see what they look like, that you don't get to see the physical extent of them. But in this case, I always get to see the extent. And here's Hubble 5, which is, again, from the Hubble Space Telescope. But what I want to call your attention to is how the shape of this object is very different. If you compare it to this one has a nice circular ring with a star in the middle, whereas this one, the star is in the middle, but you can't actually see it because there's so much more material near the center. And in fact, what you're looking at is what we call a bipolar planetary nebulae. So these are two lobes of material that have been ejected from the star in opposite directions. And in the middle, we believe, is being pinched essentially by dense material. And we'll come back to that in a few moments. Some people also call these butterfly nebulae, but I think there are some even more impressive ones we'll get into. This is the Cat's Eye Nebula. It's a very famous nebula. I think a lot of you may recognize it. Again, this is one of the most peculiar, strange planetary nebula that we have observed with the Hubble Space Telescope. And it's really one of the objects that have challenged our basic understanding of how these objects form. And everything in this image is pointing to some physics that we're missing. And I'm going to go through those objects and that evidence now. First, again, you notice the bright central star. That's common in all of these because that's the core of the sun, of what the sun once was. And then you'll notice this inner cocoon in blue with all this material in it. And then you'll see this spiral-like structure. So I'm going from the inside outside. You'll see these spiral-like structures that seem to indicate some kind of precessing flow. So if you imagine if you were holding a water faucet or a water hose and you turned up the hose and it would just like swirl around and spew water out at the same time. It's essentially what it looks like this is doing, or had been doing for thousands of years. And then when you go away from that central nebular region, you'll notice a bunch of faint rings all around the object. These faint rings are what we consider evidence of past mass loss. So past episodes where that material from that star, the sun-like star, was just ejected in bouts. So every shell there indicates a period where it went through some kind of outburst, lost a lot of material, and then calmed down, and then went through it again, calmed down, went through it again. And it kept doing that periodically, episodically, until after all of that, so I've been going from the center outwards. And when we go from the center outwards, we're going from the current status, which is this central star, to the past status. So the outer rings came first. So at one point in the past, when the star was losing its material, it was losing material in a spherically symmetric pattern. That is, it formed these shells of material. And that's what we see when we see a shell projected onto the sky. We see a ring, and that's what you see, all these rings, spherical shells of material. And then something happens, and we don't know what it is, but something bizarre happens, and the mass that the star loses becomes wildly asymmetric. You have these materials that looks like jets flying away from the object at high velocity. You have all of this spiral structure, and inside you see this ellipsoidal shell of material. So just a little brief reminder that we're talking about planetary nebulae, and this is a misnomer. They have nothing to do with planets per se, but it actually comes from the historic discovery of them. If you looked in a primitive telescope, if you looked at something like the Saturn Nebula, which I have here in the Hubble Space Telescope, if you looked in an early telescope, it would look like this fuzzy blob of material. And the main point is that when you look at it through a telescope, it has a size, and that's different than most of the objects in the night sky. Most of the objects in the night skies are pinpricks of light or points of light, stars. And so you don't really see any extent. But these objects, when you look at them with a primitive telescope, you do see some extent. The only other object that they knew about that had similar extent were the planets. If you look at Jupiter, if you look at Saturn in an early primitive telescope, it will have some extent. It will not look like a point of light, but it'll look like an object, and actually like a disk-like object. And that's how planetary nebula came to be known and came to be labeled, is that they look like planets, but they're a little bit fuzzy. And so nebula is the Latin for cloudy, and so it's cloudy planets, essentially, is the way these names came about. And so I mentioned this before, but I'll just spell it out for you now. Here's the spirograph nebula, and you'll notice it looks like a disk, and there's a star in the middle, but it's actually a shell. And it's important to remember that it's actually a three-dimensional shell. So these objects they're essentially just a sphere of material, and it's not a filled-in shell. It only has material on the outside. And so all of that material, we're looking through some of it when we look straight on the nebula, but we're looking through more of it when we get to the edges. But it looks like a disk, but in fact, it's not just a flat structure. It's a three-dimensional volume of material. So I've told you about what these objects are, what we're looking at. And I've told you the whole time that this is what our sun is going to look like when it ends its life. And the real question that you may all be thinking is, well, how do you actually determine these changes? How do you know that our sun is going to do that? Because it's going to do it in billions of years. And we haven't ever been able to see an object go from a sun into a planetary nebula. And so the way that we actually do that is by studying a lot of objects at one time. So I'll show you how you can infer that stars actually evolve by showing you this plot. So this is a plot of 50,000 of the nearest and brightest stars to the sun. And so every single point here is color-coded by what we call the color of the star. And the color of the star is essentially just how red is it and how blue is it, something just like about this. And this is actually color-coded from blue to red. A cool star would appear red. So a cool star would appear like one of these red or orange points. A star like our sun would appear like one of these green points. And then a very hot star, so a more higher temperature star, which means that it's a higher mass star, would appear as one of these blue points. In this diagram, I'm showing you the entire night sky. The entire sky, not a night sky, but the entire sky, 360 degrees and from pole to pole, so minus 90 to 90. So you can't do this from one spot on the ground. You have to do this from space. And this was done with the Hipparcos satellite, which was launched, I think, in 1989. And so this Hipparcos satellite is essentially just studying these really bright stars, nearby stars. There's a new satellite that's going to be doing even more than this. It's going to be doing billions of stars. So, like I said, these are 50,000 of the brightest and nearest stars. And so what are you supposed to take away from this? Well, because I've color-coded all these points, we can put these into a different diagram. This diagram here tells you how bright the stars are, and that's on the y-axis. So the faint stars are on the bottom, the bright stars are on the top. This tells you the color. Like I said, red is cool, blue is hot. And this is for all those 50,000 stars. And you'll see here, there's a little bit of structure. Obviously, the rainbow structure is there by design. But you'll see that the blue stars tend to be brighter. The cool stars tend to be fainter. And then there's this clump of material towards the upper, I guess, for the upper right. upper right of the diagram. So, but I want you to notice that it's hard because remember, how bright a star is depends on how close you are to it. And so the closer you are to an object, like a 40-watt light bulb, the closer you are, the brighter it appears. If you hold it at a mile away, it looks very dim and faint. You don't get a lot of photons from that object, from that light bulb. And the same thing is happening in these stars. So we're looking at their observed visible magnitude from the satellite. This is how bright the satellite sees them. And so we need to know how far away they are in order to put them on a scale that actually has intrinsic meaning to the object itself. And so to do that, we're all going to do a little experiment. I want you all to hold your thumbs at arm's length in front of you and point and look at this beautiful planetary nebulae. And I want you to close one eye, any eye, and notice where your thumb falls against the backdrop. And then just blink and close, switch the eyes that you have closed and notice how your thumb jumps across the screen. I wish I could see you all. You should all be doing this.
You look pretty silly.
So you notice how your thumb seems to jump across the backdrop of stars as you close one eye and the other. This is called parallax. It's a very useful trick for measuring distances. And so that's what this satellite is actually doing. So you were blinking your eyes, but instead what the satellite is doing is when it's in one part of its orbit, when the Earth is on one part of its orbit and it's looking at a star, it waits until the satellite is on the other, the Earth is on the other side of the sun, and then it does another measurement of the same star. And as a result, you get the two positions that your thumb, or in this case, the nearby star, seems to jump across the backdrop of stars. Using this parallax angle, you can measure how far away the distance of that star is, because you know how big the Earth's orbit around the sun is. Now, if you use this information, you can turn this diagram into this diagram. And so notice, now I've turned this visible magnitude into an intrinsic brightness of the star. And you notice how tight all of the relationships have gotten. We've cleaned up quite a bit of this spread in visible brightness, and we put it into a more narrow range. I've indicated on here the location of our sun. So this is where our sun would reside on this diagram. This is called the HR diagram, or Hertzsprung-Russell diagram. And this is the observational Hertzsprung-Russell diagram. And it tells us a lot actually about what's happening in these objects. The main line that you see going across the screen is the main sequence. And we call this the main sequence because most of the stars fall onto this line. And then you'll see down here, I've indicated also where the white dwarfs are. These are the central stars of planetary nebulae that we've been looking at. This is where they end up. But they don't go straight from the main sequence down to the white dwarf. They go through a path, and that path is what this extension towards the upper right of the diagram is. And that's called the giant branch. This is essentially the path that these objects take. So a star will start about where the sun is, and it'll evolve off of the main sequence, so the blue line, onto this purple track. And in this path, it ascends up the diagram, flies across the diagram, goes off the diagram, and then we'll come into this area of white dwarfs. And this is the path that we think our sun is going to take. Now, the reason why there's not as many stars or not many points along the track from points 5 to the white dwarfs is because this phase of stellar evolution is very short-lived. So you spend billions of years on the main sequence as a sun. You spend a few million years in these parts of the diagram where you see in the upper right. You spend a lot of time there. And then you spend relatively short amount of time. And by relatively short, I mean tens of thousands of years. But for us and for this diagram, that's nothing. And so those stars are very rare because they don't spend much time there. One more point before I go to the next slide is that these stars in the upper left of the diagram, these blue ones, these are more massive stars, and these stars that are red and faint on the lower right part of the diagram are cool dwarf stars. So the hidden variable that is in this diagram is mass, and really the brightness of the star, the temperature of the star, they're very mass dependent. And this diagram is really the first indication that there is a common engine that powers stars. So we can only measure the color, we can only measure the light from the star. We can't stick a thermometer in the star. And so this is what we see. We see how much blue light is there, how much green light is there. That's what V minus V is. We look at how bright it is. And that's all we really can get from stars is how much light they're putting out in different parts of the electromagnetic spectrum. But from that, you can infer their temperature. From that, you can infer that they all have nuclear furnaces burning in their cores. And that's all from this diagram here. So here's a little bit more information about this part of the evolution. So here I put some labels on these things. Some of these, I'm going to just gloss over them, but I'll tell you what's happening to the star itself. And maybe you've heard some of this from previous speakers. But so our sun currently is in a nice, we'll call it happy state, where it's constantly converting in its core hydrogen into helium. So it's taking hydrogen atoms, fusing them together, releasing energy, and those combined hydrogens eventually form helium. And that we'll call that the ash of hydrogen burning. And that's during its happy state. That's the state that we are in now. And it takes billions of years for it to exhaust that fuel in the core. And the core is what's most important because the core is what sets everything. And so when you're burning this hydrogen into helium in the core, you're nice and happy and you're producing a steady amount of light. And that's the phase that we're in. However, whenever you fill the core up with helium, that's when things start to go haywire. Helium takes a much higher temperature and pressure to burn. And the sun right now is just not in the core. The temperature is high. It's millions of degrees, but it's not high enough to burn helium. And there's not enough pressure to actually ignite helium. And so you just build up helium in the core, and eventually you build up so much helium that you slow down that nuclear burning in the core, and you start to evolve into what's called the red giant phase. And that's what this initial evolution off the main sequence is. We call it a red giant because although you stopped burning in the core, you still have all of this energy that you need to get rid of. And so it's getting rid of it in the outer layers. And so it's still puffing up, it's still pushing energy out into the outer layers of the star, and that causes the star to swell. Meanwhile, in the center, because you stop burning, you no longer have this strong energy force of radiation to push against gravity. And so you start to contract in the core. Gravity starts to win. Currently, we're in a nice, what's called hydrostatic equilibrium, which is where gravity and the radiation pressure from this nuclear furnace are in balance, and so the star is nice and stable. But once you knock something out of stability, you start to experience change, and that's what the red giant indicates. The red giant phase indicates. You start to contract the core, and as you contract the core, you start to heat it up, and you start to build the pressure, and eventually you can ignite that helium that's in the core, and that's called the helium core ignition. It usually happens in a flash, and we call that the helium flash. And helium, because it burns at such higher temperature, it burns very, very rapidly. And so you only stay in this period, in this phase for a short amount of time. And then you go into a steady helium burning phase that's called the horizontal branch, indicated by 0.3. And then you ascend onto what's called the asymptotic giant branch. And this asymptotic giant branch phase is really what we're seeing when we look at images of planetary nebula. We're looking at all the material that the star loses during the asymptotic giant branch phase. And we know this because when we look at asymptotic giant branch stars and we measure their circumstellar environments, we see that they're losing tons and tons of material. they're losing about 10 to the minus 4 solar masses per year. And that may seem like a small number, but if you think about it like this, currently our sun is losing mass. It's shedding material into space, and it's doing it at a rate of 10 to the minus 17 solar masses per year. 10 to the minus 17. That's a really small number. Now, think about in this AGB phase, now you're losing it at 10 to the minus 4 solar masses per year. That's 13 orders of magnitude increase in the mass loss, and it's a significant amount of mass loss. And all that material is going into the circumstellar environment. And that's essentially what's going to become the planetary nebula that we see in all the images, all that material that's being lost during the AGB phase. Now, after the AGB phase, you'll notice that I don't have a line connecting these points. And I didn't put it there because we don't know exactly what happens, but we know that the phase goes from AGB into this post-AGB planetary nebula phase. And I'll go into a little more of why we don't know what's happening there. But essentially what happens is we form this nebula via fast wind. We call it a fast wind, but we don't actually know what the trigger is of that fast wind. That fast wind plows into the AGB material, sweeps it into a shell, and that becomes the planetary nebula. Meanwhile, that central core that was burning helium is just so hot. It's essentially an ember, so like a piece of coal you pull from a fire, and it's just radiating residual heat. And that heat is actually ionizing this nebular material, and it creates the beautiful images that we see in the planetary nebula phase. And after that, your planetary nebula fades, and then you end up as this white dwarf, which is just going to cool, essentially for the age of the universe. On the bottom, I have a little diagram showing you the elapsed time, showing you this approximately how long each of these phases last. But I'll go on because I'm worried about time. So, like I said, you're losing tons of mass, and you're losing most of that mass during the AGB phase. And to put some perspective on how much mass you're losing, so I told you that the white dwarfs are about half a solar mass, and they can start at they started with about 1 solar mass, and so you end up losing half a solar mass. So half the mass of our sun spread all around you into this planetary nebula. It's also possible that you could be 8 solar masses and still end up going through this evolutionary phase. In that case, you'll end up with a white dwarf close to about 1 solar mass, but not much higher than that. And so if you think about going through that phase, in that case, you've lost 7 masses, 7 times the mass of our sun have been shed into the environment around you. You've essentially just sloughed that material off and spread it out into space. That's a significant amount of mass, and so there's a lot of material. It's all been enriched through this hydrogen and helium burning, and it's all been liberated into space. And essentially, it continues to spread and disperse into the universe, into our galaxy, and it can enrich the chemistry for the subsequent generations of stars that form from it. So I showed you a little bit about the Hipparcos observations and what we learned from that space telescope. We learn about stellar evolution, essentially. But now I'm going to show you a little bit more about what we've learned from some more of these great observatories, they're called. So here are 3 of NASA's 4 great observatories: the Hubble Space Telescopes, which we've seen images from; the Chandra X-ray Observatory, which is who pays my bills; and the Spitzer Space Telescope, which I show you here on the left. So I'm going to focus again on the Hubble Space Telescope. What we've really learned from Hubble Space Telescope is the variety of shapes that planetary nebula come in, and they've really challenged our understanding of how these objects form. So I have here an ensemble of a bunch of elliptical, mostly elliptical structures. So you see you can put them into some kind of morphological class. You could call these all elliptical, but maybe the cat's eye doesn't belong in there. But you'll notice that there's not very many round shapes, and the only one on here that looks round is the Eskimo Nebula. But in fact, if you study the Eskimo Nebula and its material a little bit more, you'll actually learn that it's probably one of these bipolar objects, but we're looking at it straight pole on. And so you don't actually see the two lobes, you only see the one lobe that's pointing towards us. Here's a bunch of planetary nebula that all have this bipolar structure to certain degrees. You'll notice on the far left, I have an object that has a very broad waist. It doesn't seem to have a very pinched, narrow waist like the extreme cases that you see going further down to the right. And then you'll see some that just look like they're essentially in the midst of breaking apart whatever it was that was holding them in the core. They're essentially losing that tight waist, and maybe they're evolving from this state into the previous state. We really don't know because, like I said, it takes a long time for these objects to actually evolve. So essentially, we've come up with these classifications. We call planetary nebula either round or elliptical, hourglass or bipolar, or sometimes we even find a few multipolar objects. And we're trying to understand why we don't see very many round planetary nebulae. There are a few here or there, but we don't see very many of them. And so this really led to essentially the state that we are now in the community of trying to figure out how planetary nebula form and whether there's something peculiar about their formation that we have to, that may force us to revise our understanding of these objects. So to give you an idea of the thinking of how we've come to the new paradigm, here's a deconstructed example of what this bipolar object looks like. You have these two lobes, you have the pinched waist, you have the star in the middle. And so what we think is happening, and we can show this with hydrodynamical simulations, is that there is some kind of torus around that central star. And that torus is confining the material. And so I showed you earlier, I talked about how during the AGB, you lose all of this material, and you lose 10 to the minus 4 solar masses per year. All that material goes into your surrounding environments, and you lose that material. And so that material should be lost spherically symmetrically. That is, should not have any preferred direction for mass loss unless there's some additional constraint, some additional physical mechanism that's causing it to be lost asymmetrically. And so one idea is magnetic fields. If you had a magnetic field and the mass was preferentially being lost along the poles, then you might explain that you're losing mass. But we've tried very hard for decades to look for this evidence of this magnetic field in AGB stars, and we just don't see any evidence that there are magnetic fields. The hope hasn't been given up that magnetic fields could solve it, but we are now starting to explore alternative scenarios. And the one that a lot of people support is this idea that there's some kind of torus, and we call it a collimating torus because it collimates that mass loss. It causes that mass to be lost preferentially along the poles, and it ultimately forms these bipolar planetary nebulae. Of course, if you have your critical thinking hat on, you'll notice that I haven't really solved the problem. I've only replaced one problem with another one, which is, where is this torus coming from? It's okay to make the assumption that maybe there's a torus, but now we actually have to explain the torus. But quickly, this is just a little illustration to show you how we think this mass loss happens. The mass loss is spherically symmetric from the star, but then it's actually reshaped by this torus. And so where we think this torus is coming from is possibly coming from interacting binaries at the center. And we call this the binary hypothesis. And essentially what we're saying is that in order to form a bipolar planetary nebula, maybe you need to have a companion to your star. And so when you're losing mass, it actually builds a circumstellar torus, a circumbinary torus. That is, when you're losing mass and you're in a binary system, the orbital motion of the binary system will cause that mass to preferentially be lost into the equatorial plane. And that's happening during the AGB and during the red giant phase. So you build up this torus so that when you do launch your fast wind that sweeps that material into the bipolar planetary nebula. When you launch it into this torus, and it causes it to be collimated into these bipolar outflows. And if we take this binary hypothesis and we extend it, we can come up with a number of scenarios where having a binary companion to your mass-losing system, in your mass-losing star, the star that becomes the central star, having a companion, you can come up with different scenarios where you end up reconstructing all of the shapes that we see in planetary nebula. So I've talked to you about how you can form this bipolar planetary nebula by building this equatorial torus. But it's also possible that if you end up in a close binary system, so two stars that are really close to each other, orbiting each other, when one of them starts to swell into its red giant phase, that second star is actually going to fall inside of that red giant. And so for a moment, the two stars will appear as one, and you'll actually, inside that environment, that secondary star will start to experience a lot of drag from all that material that it's now found itself inside of, and it'll cause the orbit to decay. And as the orbit decays, the star wants to merge, in which case it'll merge, and you can go through a path where you eject later on, or it'll actually transfer some of that orbital energy into ejecting this common envelope, this outer shell of material, and that can form an elliptical planetary nebulae. Stellar mergers are hard to understand, and they're still understanding them is still in their infancy. But we seem to see evidence when we look at the central stars and we look at their nebular morphologies. We see some evidence that could indicate that this is actually what's happening. And then we have another scenario where if you have a wide binary, the influence of your companion is not so difficult, it's not so extreme, and so you could end up having a more gentle distortion of your mass loss, and you could form these large elliptical planetary nebulae that way. So really the evidence to test this hypothesis comes from discovering the binary systems, discovering how many of these stars actually have binary cores. And that's what we've been trying to do. But I want to point out one important thing is that I've said this whole time that this is the phase that our sun will end up in. But our sun is not a binary, and so does that mean that we're not going to have this beautiful end state of this beautiful death where we shed this material into space and we form this beautiful planetary nebula? And it turns out, and this is based on simulations by a colleague of mine, he showed that something the size of Jupiter has enough angular momentum stored in it so that when our sun goes red giant, if Jupiter falls in, it can undergo this entire process where you eject this common envelope and form this planetary nebula. So hope is not lost for a beautiful death. Okay, so that's what we've learned from Hubble. We've learned essentially that these shapes are nothing like we expect, and now we're actually looking at these objects with the Chandra X-ray Observatory. And this is the work that I've actually been doing and that I've been spearheading. I started in my PhD thesis, and now I'm going to run through some of the evidence of show you what we see with X-rays and how they're informing this picture, this binary hypothesis. Here again is the Cat's Eye Nebula in the Hubble Space Telescope, and I'm going to show you what it looks like in X-rays. Notice where the X-rays fall. They're all within this inner shell of material, and they're also coming from the central star. And that information is key because it's actually telling us a lot. It's confirming a lot of what we understand how these planetary nebulae form. They form from this collision of this fast wind with this slower moving material, the AGB material. And that is seen when you look at these objects. And here's a bunch of them that we looked at together. I'll blink back and forth just to show you that the X-ray emission is all coming from within these inner shells. And so that X-ray emission we call the hot bubble. And it's a hot bubble because it's the result of this collision, this shocked gas. And it gives us clues that we are on the right track of understanding how these objects form. But the thing that puzzles us about these objects are the point sources in the middle. So I told you that these central stars start off as something like the temperature of the sun. But as they evolve, they get hotter and hotter. And that's because we're looking at the residual core, that residual hot core of the star. But they don't get hot enough to emit X-rays that we see in these images, these point sources in the middle, these little dots in 3 of these objects. They don't get hot enough for those points to be explained. And so what we're actually looking at, what we've deduced that we're looking at from these X-rays from the central stars, not the extended emission, but the points in the middle. We're looking not at the central star itself, but we're looking at X-ray emission from the companion to that star. And in 3 of these, we know that they have companions. And when we study their companions and we study the X-ray emission is consistent with X-ray emission coming from their companions if their companions are active. And by active, I mean that they have a lot of magnetic activity going on. Not the star that formed the planetary nebula, but the companion to the star. In that scenario, we can reconcile that X-ray emission and that activity with this idea that these stars have gone through a common envelope, meaning that they were orbiting each other at a very small period. One of them fell into the other as it swelled into a giant, and then it ejected that material and it emerged as a binary that is zooming around its companion. In some of these planetary nebulae, we see orbital periods less than a day. So a star flying around its parent star in less than a day, doing a complete orbit. It's just mind-boggling, but you can only get that. You can only get such a binary system if you've undergone common envelope evolution. And if you are in such a short period binary, chances are you have been spun up, and as a result, you are more active than you would have been. And that's what we think we see from these X-rays that we've studied. And so these X-rays give us clues into this binary hypothesis, and they seem to indicate that in some cases we can explain that binaries are responsible for forming the asymmetric structures that we see in these objects. Here's the 4 composites, the Hubble Space Telescope with the Chandra X-ray emission, just to show you where the X-ray emission resides within these bubbles and also from their central stars as well. So I'm going to conclude now showing you what Spitzer Space Telescope is showing us. So here's the Cat's Eye Nebula in the Hubble Space Telescope again. I want to remind you that optical emission is easy to focus. Infrared, which is longer wavelengths, are a little bit harder to focus, and so don't hold on to your seats because you won't need to. This is what we see with the Spitzer Space Telescope. Again, you don't see as good of high fidelity an image as this, and that's because these are longer wavelengths. They're harder to focus. You need a better telescope, and we are going to have one soon with the James Webb Space Telescope. But if you step back from that inner part, this is what you actually see in the entire Spitzer image. So there in the middle is what we've been looking at the Cat's Eye Nebula. But notice this blob of material off to the upper left, and notice there seems to be evidence of additional material out there. There's actually, in fact, a ton of material out there. And this is an optical image, a very, very deep optical image in H alpha. And you can see there's tons of material out there from the mass loss. Some of it is being ionized by the central star. And then you see in the middle, the thing that we've been calling the cat's eye. We're only looking at a small part of it. There's a lot more to look at. And so what we're actually looking at in this olive looking diagram is we're looking at essentially all types of matter. We're looking at this very hot X-ray gas that's 10 million degrees Kelvin. And then we're looking at the optical emission, which is what we've mostly been calling the Cat's Eye Nebula. That emission is at 10 to the 4 Kelvin. And then as you go further away, you get cooler and you start to form molecules. And there's some molecular hydrogen really close to the nebula. Then you start forming dust and molecules in the infrared, and that's really cold material. And so really, in order to understand a planetary nebula, you actually have to study it across the entire electromagnetic spectrum. Because if you just look at one part of the spectrum. If you look at the X-rays, you won't see the nebula. If you look at the optical, you won't see the X-rays. You won't see all the other information that all of these wavebands tell you. And it's really the direction that we're headed in the community are these multi-wavelength studies of objects to really piece together the entire physics from the cores and the hot cores all the way out to this cold, low density material, much further out from the central stars. And so I'm going to end with the picture of the Helix Nebula, and I just want to show you what it looks like in Spitzer. Isn't that beautiful? Notice how many more stars you see in the core, in the central region. In the optical, it looks bare. You see 3, 4 stars. In the infrared, you see a lot more cool stars that are probably behind the Helix Nebula and peeking out. And now notice this is another Spitzer combination. Spitzer had a bunch of bands, so you can't do them all in one. This is another one. There's a really, really cold spot coming in the middle. That's what the red is indicating. And now this is a composite from Spitzer, WISE, which was a short-lived infrared space telescope, and GALEX, which is a UV telescope, showing you, again, the Helix Nebula as we've been seeing it, and showing you all how these things overlap. But then, again, you can step back, and you can see this. You see even more information. You see stuff that looks like bow shocks to the left of the image, some kind of indicating either the motion of this nebula through space, through its interstellar medium, or indicating the ejection of something. Just so many questions just from this image alone that we have to address and that we have to study better in order to understand what's going on in these objects. So with that, I'll come back to you.
There he is. Wow, that's amazing. Let's give our speaker a round of applause. Do we have any questions for our speaker, Russell?
So you said that the Spitzer telescope has several bands that it can look at. I was just wondering, how exactly does it work? Because normally when I hear bands, I think of like an antenna.
You think of an antenna, okay. So we typically use, bands, if you're studying radio astronomy, bands typically indicate that you have a different type of receiver on your antenna. But typically we use this terminology band to indicate any segment of the electromagnetic spectrum. We tend to call these photometric band passes. It may be a leftover term from the radio days. I'm not sure the origin of why we use bands, but it's any segment of the electromagnetic spectrum. The Hubble Space Telescope images, for instance, are taken in narrow band images, and that's focusing on a few angstroms of light centered on some wavelength. The GALEX images are taken in far UV and near UV bands, and those are very broad, hundreds of angstrom wide bands. The X-ray observations are actually interesting because in the X-ray observations, you actually measure individual photons. And so think about that for a second. You don't integrate all the light within one band. You just get a photon. It interacts with the detector. That interaction generates an electron cloud. And then you count the number of electrons in that electron cloud, and that tells you what the energy of the incoming photon was. It's really kind of amazing to think about that we can do that, and we can only do that because X-rays are rare. They're not very, these sources are not very bright. So maybe 1 in 30, 40 frames, you actually see a photon, and so you end up observing for hours just to get a few photons. Other questions? Yeah.
Yeah, you mentioned some of the new telescopes that are going to be going on, like the W-First telescope. What are some of the, or the James Webb, you mentioned that. What are some of the things that you're aiming to find out from the new infrared telescopes that are being launched?
Right. So one of the biggest things, so we talked about photometric bands, and photometric bands are useful because they give us a general idea of what the object is emitting in that specific range. But what we're going to get with new telescopes is we're going to get better spectrographs. And spectrographs actually disperse the light. And when you disperse the light, you get so much more information. You get access to a bunch of emission lines. Those emission lines will tell you the composition of the gas that you're studying. They'll tell you how much hydrogen, how much helium, how much carbon there is. They can also tell you the ratio of those lines can tell you how hot the plasma is. It can tell you how dense the plasma is. And so all of the physical properties that we try to understand, we understand by studying the spectrum. And so really these newer telescopes are going to give us a better idea of the spectrum. And so Spitzer did have some spectrographs, and we did get some information from that, but the James Webb telescope is going to have such a larger collecting area that it's going to be a larger telescope that we'll be able to actually get a lot more photons in our spectrum. And so we'll actually get a good idea of the physical conditions in these objects. And all of that ties back into, okay, well, if you have these abundances, does that make sense with a single star paradigm, or do you need a binary to have these different abundances? All of these things will come back together. And the spectral lines will also tell us something about if there are magnetic fields in the nebula itself.
Thanks.
So how many of the students here have taken like an astronomy class or an astrophysics class? Took Dr. Burris's astrophysics class a year ago, last year? Last summer? Okay. So some background with astrophysics, but not a lot. The lead-in to that HR diagram that you did at the beginning was one of the best I have ever heard. And how you started with the wide field view of all the stars and the temperatures, basically, the colors. And then from that, put it together and then said, oh yeah, but if you're closer or farther away, the intensity changes, we have to fix for that. And then it was just beautifully done. Very, very nice.
I spent a lot of time on that.
That's perfect. That's the best description I've ever heard. My question is, so for that binary hypothesis, how long has that sort of been in the literature? What's sort of its age?
Mm-hmm. So it's been tossed around as possibly the way you form these bipolar planetary nebulae with these tight, narrow waist and bipolar lobes. It's been around to explain those for quite some time. I would say maybe in the late 90s, that idea came about, and it mostly came about because of symbiotic binaries. Symbiotic binaries are very similar evolutionary states. You have this white dwarf and then you have this giant. So they're essentially maybe what would come after the planetary nebula phase. And in those cases, when you study them, you see that they tend to form these bipolar planetary nebulae as well. And so that gave us the idea that maybe that's happening earlier in the phase. And so that started there. But it didn't get much traction in the community because when we looked for the binaries, we couldn't find them. We had about a binary fraction of like 5 or 10% up until about 2005. And in about 2005, people started to look really hard for the binaries, and we started to find them. And we've just slowly ratcheted up the number of binaries that we have, and now we're at about 23% of them. We know they have binary systems. And so the real difficulty about this hypothesis is that you can't prove something isn't a binary. You can only prove it is a binary. It's hard to do it the other way. And so really until we have the best observations, we can't really say whether or not they're all binaries or not. And so we're going to try, and we're going to try to figure that out. And then we also have some really peculiar objects. We call them Wolf-Rayet central stars of planetary nebulae. Wolf-Rayet stars tend to be massive stars, and they're peculiar because they have emission lines coming from the central star itself. And that's unusual, and it indicates that there's some kind of material directly surrounding the central star. And we see that in some planetary nebula, and some people interpret that as evidence of a companion that was ripped apart and merged onto the star. And now it's this puffy material directly on the star that's emitting this emission line. And so that may be an indication that that was once a binary and is now a merger product. So there's a lot of ways, different ways to actually figure out that binarity seems to be a really strong criterion.
Lucas.
So you mentioned briefly that if our sun was to go into the planetary nebula, that Jupiter would be enough mass to do it. But in the X-ray images that you would see, like if we were to be observing our own star, planetary nebula, and how would you detect Jupiter afterwards? It's not
right. That's a good question. We wouldn't detect it, right? That's a really good question. We would not detect it because so we also wouldn't detect some of these merger products either, because that companion is no longer there. And so the X-rays, well, the way we've been using the X-rays is we say, oh, look, there's the source, and it's a hard X-ray source, meaning that it's a high temperature source, so it can't be explained by the primary. So then we'll give that evidence to fellow observers and say, look, you should look at this star more carefully. They'll look at it more carefully, and then they'll find the binary. But it doesn't work if you're a merger product. It doesn't work if you're planetary nebula formed from a planet in fall. So yeah, that does lead to. But a curious, interesting thing that does happen is in the Helix Nebula, there's a really bright central star X-ray emitting source there, and we don't know what it's caused from, because it's so close to us that we've looked at it with Hubble. We've looked at it with Spitzer, we've looked at it with everything, and we don't find any evidence for this companion. But what we do see is a debris disk, which suggests to some people that maybe it's ripped up a planet, and that planet is slowly dropping material onto the star, and that's what's causing the X-ray emission that we see.
So what advice might you have for current undergrads who are interested in this kind of work? What advice would you give them for how to learn more, or to get into doing an RU program or graduate school in this area?
Yeah, I think that RU programs are really good experiences, especially if you don't have a lot of active research going on at your home institution. I mean, I did a couple of RU programs when I was an undergrad, and it really helped define what I wanted to study. It really actually helped me decide that I did want to pursue this line of work, because it is something that you don't really know what it takes until you've done the research, and it really takes the research. I mean, we put a lot of emphasis on taking math, taking physics, taking courseworks, learning how to program. We put a lot of emphasis on those things, but those are the things that you can learn, that you can learn how to do. The thing that you don't know you can do until you do it or try it is the research aspect of it, because it really does take I guess it takes perseverance, because you're going to fail a lot. You're going to make you're going to go down the wrong road a lot. You're going to try something, it's not going to work. You're going to have to go and try something else. You're going to have to abandon something that you really thought was a great idea, and then abandon it and go on to something that actually works. And that having that ability to persevere through those types of obstacles really affects whether or not you can actually succeed at being an active researcher. And you can't do it on, what's that?
So I was going to say the more experiences and different types of research, or getting your hands dirty in different labs in different institutions, is a good experience to kind of hone.
Definitely. And it's also good because, I mean, to be completely honest, sometimes you'll have a great advisor, and sometimes you'll have a terrible advisor. And it's not that they're not terrible scientists. They're just not you and them, I mean, you're dealing with personalities, your personality, their personality, and you really have to find the ones that work, the personality that meshes well, where you have the same, you don't want the exact same perspectives, but you want to be able to communicate. and it's really important to have somebody that you can bounce ideas off and that will appreciate those ideas as well. And that really, I mean, if your first experience is a bad one, doesn't mean the next one's going to be bad, right? So that's why I really enjoyed doing and recommend doing research as an undergrad, because you get to explore essentially all of that.
Yeah. So you did your undergrad at UT Austin.
I did.
And then you did a couple REUs. Where did you go to REUs?
So I did my first REU. So well, actually I should back up. So I actually started in community college at San Antonio College in San Antonio, Texas, and I started San Antonio. Yeah, I started as an accounting student. So I was doing accounting for 2 years, and I decided that I didn't want to do that because, I mean, I was doing well. I was doing very well in my classes and everything, but it was not at all what I wanted to do. So but I had no idea that you could be an astronomer as a career. And so it was when I took my intro science course in astronomy that I really liked the class, and my friend of mine told me that I should actually do that. And I said, you can't do that. So I asked my professor about it, and he said, yes, you can. And this is what you do. And he said, go apply for REUs and go take math and physics. And then after you're done with that, you'll figure out what it takes. And I was like, okay, good. So that's what I did. It took me 2 years to catch up. I caught up, transferred to UT Austin, and then I finished my bachelor's degree there. And at UT Austin, I did my first REU program just down the road from here at the MIT Haystack Observatory, which is a radio facility that has a big radome. And there I worked with Alan Rogers building an electronic noise calibrator. So a purely engineering project, but for a small radio telescope that they built to teach people radio astronomy. And they still use it today. It's still distributed. Every once in a while I get an email with someone asking why I did this and that. And I was just like, I don't know, I was an undergrad. They use my REU report as the manual on how to build this thing.
Oh my gosh. You're immortal.
Yeah. And then just the other last November, I was in South Korea, and they have one of these small radio telescopes there. And I looked at the vertex of the dish, and I saw my electronic noise calibrator there. And I said, "Hey, where'd you get that from?" And they told me, and I was like, "Yeah, I made that. I designed it." But that was my first REU. After that, I did an REU at CTIO, Cerro Tololo International Observatory, which is in Chile. That was during the Chilean summer, so it was during my winter. So I actually had to miss class for that REU, but I was very happy for the opportunity, so I took it anyways. And that was a good REU program. That's when I actually started doing planetary nebula research. I did a lot of observing there at the observatory, which is just beautiful. I missed that part of astronomy a lot because now I mostly use satellites, so I don't really get to go observing. But I do have an observing run coming up Thursday. I'm not going, my collaborator is, but it's also in Chile. And then after that, so that was a very, in about like a period of about a year, I did these 3 REUs because one summer, one winter, and then the next summer. And that last one I did was at the Southwest Research Institute in San Antonio. And I chose that one because I wanted to stay home because I knew I was going to grad school and I wanted to be with my family for that last summer. So I did the REU program there. And there I studied the aurora of Jupiter using the Hubble Space Telescope. That was a really cool project. And then I went to grad school.
Wow. So you knew after working on planetary nebula that was what you wanted to go to grad school in? Did it impress you that much, or was it later on that you also, in grad school, knew this is it?
No, the places that I applied for grad school were based on who was doing that research in the U.S. So that was where I wanted to go. So it was that experience that was really, really eye-opening for me because I don't know, it's beautiful, but it's also there's so much stuff to do. There was the community that community in particular, planetary nebula, is it's relatively small. So it's not as widespread in the U.S., but there's a big community in Mexico and Spain, and in other parts of Europe, and that I mean, yeah. So that gives me an excuse for traveling a lot, but it also means that it's a really international community with a lot of different perspectives, and I really enjoyed that a lot when I started working in that community.
Cool. So apply for REU,
Yes.
right? Do
Yeah.
it.
And even now, there are lots of opportunities for. I mean, there's lots of opportunities for amateur astronomers, and so you don't have to be doing active research, getting paid for it. You can contribute to other projects. Like there's a project called Galaxy Zoo that people just classify galaxies, and they're also making discoveries. We've heard in the American Astronautical Society meeting, we've heard from amateurs actually talking about their discoveries, because they're very actually, some of them are very breakthrough discoveries. There's also the AAVSO, which is just up the street from here. It's the American, what does it stand for? Variable Star Observers. American Amateur Variable Star Observers.
Okay.
And they're essentially reporting magnitudes of stars, monitoring bright stars that are variable. I use their light curves all the time to help me plan observations, and also for knowing how bright my objects were when I studied them with X-rays. There's plenty of opportunities to get involved, to get your hands on some data. All of the NASA missions have public data archives. And so you could go download the Hubble Space Telescope images I've been showing you. They won't look as pretty because they're just going to be black and white, but you can download them and you can do some analysis on them. The X-ray archives are also available. I made most of my PhD projects have in their titles, the publications have in their titles, serendipitous discovery of, because I was just looking through the archive and looking for my objects, my planetary nebula, and looking for them and saying, oh, look, there it was accidentally observed, because the field of view is big, and so you can't keep objects out of it. And so they were looking at this galaxy, but just off to the side is my object, and look, it's a detection. And by putting those together, I actually built this large international collaboration that I co-lead with my PhD advisor, called the Plans, or the Chandra Planetary Nebula Survey. And it was built originally from these serendipitous detections that showed that, look, they emit X-rays, here are their properties, here are the questions we have, and this is why we want you to give us more observations. And it works. So we're now in the era where data is no longer the limitation. You have access to the observations. You can do stuff with the observations. It's really the people power that we need. We need the people to do the research, to learn how to study the observations and to do them. And we're entering that era faster and faster. As the Large Synoptic Survey Telescope comes online, there's going to be plenty of opportunities for smaller institutions to get involved. There are already people who are working on making programs for smaller institutions, because we're going to have, terabytes of data an hour. It's going to be absurd amount of information, and we just need the people to actually make the discoveries.
So we've heard from Pamela Gay. She basically runs the CosmoQuest, and they've got a lot of lunar and Mercury mapping sort of citizen science projects. Right. Is this sort of what you're also thinking about? Is that there'll be like a citizen science component to looking for these X-ray objects in the data? Helping identify them?
We haven't come up with any citizen science projects yet. That doesn't mean that we won't. It's now that I'm here, I can actually say something like that, bring something up like that. But we haven't come up with any yet. But we're still getting our Chandra source catalog together, which is essentially looking at all our observations and pulling out the observations and the detections of objects, and publishing that material into a catalog that people can then use to do their science. And so once we have that out and complete, and we're talking about maybe in 6 months we'll have that finished. Once we have that out, then we will start to actually think about ways that people can start doing citizen science on that data.
All right. Well, do we have any other questions? Let's thank our speaker one more time. All right. Well, thank you very much. This has been amazing. Really a great seminar.
Good. I'm glad.
Thank you. I'll send you a follow-up email later tonight or tomorrow. And again, thank you very much.
Okay. Bye.
All right.
Thanks for coming.